Hello everyone, so today we're going to go over section 2.2, reflections and stretches. So reflections create mirror images of graphs over some line of reflection, usually the x or y axis. So like translation, they do not change the shape of the graph, but unlike translation, they do change, well, that is to say, they may change the orientation of the graph. So there are two types of reflections that we will look at. The first is when the output of a function is multiplied by -1, or if the y is replaced by -y, the result of y equals f of x becomes y equals negative f of x, and that is a reflection of the graph over the x-axis. So if we think about it as a mapping from P comma Q, then instead we'll have P negative Q. Similarly, when the input of a function is multiplied by -1, or if the x is replaced by negative x in y equals f of x, the result is y equals f of negative x, and it is a reflection over the y-axis. And the resultant mapping would be negative p q. So let's look at some examples. So here we have two graphs, and we will reflect one over the x-axis and the other over the y-axis. As such, the first graph, instead of y equals f of x, we will have y equals negative f of x, or negative y equals f of x. Okay, so the original graph has these 5 key points. And of course, we have here the x-axis. I'm going to draw that in. Actually, use a different color here. Okay, so this is the x-axis. So as the function may suggest, the y values becomes negative versions of themselves. And so the resulting graph would have these 5 points instead. So for example, instead of -4, -2, the image would have -4, +2 as one of its points. And we do the same thing for the rest of the graph. So 1, 2, 3, 4, and 5 points. And then we can connect the points together to form a graph. And you can see, and we can see that it is the same shape as the original graph, but it is upside down. Of note are these points here, -3, 0, this point here, and there's a couple more. What is important about those 4 points is that they appear on both graphs, and such points are called invariant points. Okay. So the original domain of this graph, that is to say, the domain of the original graph would of course be -4 to +5. And the range would be from -3 to +2. So the domain and range of the new graph, notice that the domain does not change because the x values did not change in our graph, but the range will now be -2 to +3. Which makes sense because this -3 here becomes +3, and this 2 here becomes -2. Right. So on the right-hand side, we'll have here the y-axis. So we have the same 5 points once again. 1, 2, 3, 4, and 5. However, this time instead of changing the y values to the negative versions of themselves, we are changing the x values. So this point, once again, we'll start at the bottom left, -4, -2. In the image will become +4, -2. And again, we can do the same thing for the rest of the points. So here we have, instead of -2, 2, we have point 2, 2. Here, 0, -3 will still be 0, -3. 3, 1 will become -3, 1. And finally, 5, -1 will become -5, -1. Oh, didn't mean to use blue here. All right, let's change that. Sorry about that. Okay. Let's see here. This point. All right. There we have it. And then, once again, we connect the points together to form a graph. Wait, that doesn't look right. Must have done something wrong. Right, and then, oh, right, -2, 2 becomes +2, 2. Okay, that's better. It's always a good idea to examine the work as we go through questions instead of just blindly copying. So in that case, it worked out. So as we can see here, the graph looks the same, but it's reflected over the y-axis as we expect. In this case, we have 1 invariant point, 0, -3. And we'll be looking at a more precise definition of what a invariant point is in just a little bit. Okay, so the domain this time is what changes, of course. So instead of having -4, +5 as the domain will now be -5 to +4. Using the wrong colors for all these. It's not a big deal, but do want the graphs and the domain range to be color matched. So, and then the range is from -3 to +2. Okay. So that's an example of how we can reflect graphs over both the x-axis and y-axis. So next up, we have some algebraic examples. See here, the point A, which has coordinates 2, -3, lies on the graph of y equals f of x. What are the coordinates of its image A prime on the graph of, and then A, B, and C? So let's look at each one. First example here, this is a reflection over the x-axis. As such, the new coordinates would be a prime. 2 remains unchanged, the x coordinate, but we take the negative value for -3, which makes it +3. Okay, likewise, in the second example, B, this reflects over the y-axis, of course. And the result would be a prime as -2, -3. Okay, because we essentially multiplied the x coordinate by -1. And finally, this one is new. Example C, this is reflected over both axes. So both the x and y values will change. So this would be a prime with coordinates -2 and +3. Okay. So next up, we are looking to determine equations of an image graph after reflection. In example 2, we're given the equation for g of x. G of x is equal to -2x cubed plus x squared minus 5x minus 3 right here. All right, so if there's reflection in the x-axis, what happens? Well, that means we would have -y equals f of x, or y equals to negative f of x. Oh, sorry, that's not quite right. We want g of x here. But the idea is the same, so just going to change that. Right, so that means instead of this original equation here, what we'll have instead is y equals to negative g of x. So g of x, of course, was -2x cubed plus x squared minus 5x minus 3. So we can simply distribute the negative sign through the parentheses there. And so y is equal to 2x cubed minus x squared plus 5x and then plus 3. And if we were to graph both g of x here and this reflection, we will see that they're mirror images of each other over the x-axis. Sorry about that. There we go. So if there's a reflection instead in the y-axis, then of course we will have y equals to g of -x. So what that means is every instance of x will be replaced by -x. So we will have -2 and then -x cubed plus -x squared minus 5 -x and then minus 3. And after some simplifying, of course, -x cubed will still be negative, and then multiplied by -2 will result in positive 2x cubed. -x squared is just going to be positive x squared. Notice here the -5 and the -x, the negative signs will eliminate each other, so we have plus 5x and then minus 3. Okay. So a little bit different, but the idea is very similar. Alright, so let's see if I can fix this here. I just want to move this text. That's a bit better. Alrighty, so next example, what transformation has occurred to change y equals x squared plus 2x to y equals negative x squared minus 2x? Okay, so in this case, what we can do is factor out the negative sign from both the first and second terms, which will result in negative, and then in parentheses, x squared plus 2x, which of course is the same as negative y equals to x squared plus 2x, which when we compare to the original function, y equals x squared plus 2x, the y has been replaced by negative y, and we know this is a reflection over the x-axis. Okay. So next up, very similar example as to example number 2. It says here, write the equation of the image of y equals 10 to the x power after reflection in the y-axis. So the easiest way to think about this is if it is a reflection in the y-axis, then we have y equals f of negative x. And since we're here, a reflection in the x-axis means we have negative y equals f of x. And then instead of the generic f of x function, we look at the specific function that we're dealing with. So in this case, we'll have y equals 10 to the negative x power. And on to part B, this could be written as either negative y equals to the square root of x, or simply y equals to negative the square root of x. Either or is acceptable. As we looked at before, here's the definition of an invariant point. An invariant point is a point on the graph that remains unchanged after a transformation is applied. So any point on the curve that lies on the line of reflection is an invariant point. So that's just a definition of what we talked about on the first page. And that's it for today. So thank you for listening.